To begin our analysis of special relativity, it's instructive to think about time. Our watch is an analog instrument, the same as a voltmeter. But the hands of our watch are not an analogue of time. For every rotation of the Earth, our hour hand rotates twice. Consequently, our watch is an analogue of the rotation of the Earth. So, where does this leave us with our understanding of time? The answer to this question is nowhere. Einstein said that time is a stubbornly persistent illusion. To illuminate this idea, first take the example of simultaneous events. The viewers of these fireworks report the events differently. This is because sound travels far more slowly than light. For simultaneous event 1, the two viewers on the left report hearing the sound at the same time. For simultaneous event 2, the two viewers on the right report hearing the sound at the same time. If we had a moving reference frame, for example a train, we can produce a similar simultaneous perception of sound through the movement of the train. The observer outside the train, in reference frame 1, reports two separate explosions. The observer on the train, in reference frame 2, reports a single explosion as he passes through the compression waves simultaneously. Perceived sound events may appear simultaneous in one reference frame, but not in another. Light events on Earth all appear simultaneous. This is because light travels so quickly. Astronomical distances are required to handicap light a bit, and they do a good job at this. A flare appearing on the Sun appears to us on Earth 8 minutes later, and on Mars 13 minutes after that. So, as far as simultaneous astronomical events are concerned, we need to ask ourselves, simultaneous to what? For special relativity, the answer to the question is this: a non-accelerating reference frame. Let's look at simultaneous events in a non-accelerating reference frame. These two astronauts are approaching a large black asteroid in the foreground. They pause when they're both at an identical distance from a laser transmitter on the Moon in the background. They are now both in the same non-accelerating reference frame. A signal is fired from the transmitter on the Moon and the light reaches them simultaneously. This is Einstein's definition of a simultaneous event. Here, light is the universal metric for distance, the light second, and light year. It is also the universal metric for time, the time taken for light to travel a second or a year. A second simultaneous event occurs on the planet when the signal from the astronauts is returned. We now examine a very odd feature that occurs in a reference frame moving close to the speed of light. So we begin a thought experiment with a train carriage for a reference frame and a tennis ball for a photon. The purpose of the experiment is to analyse a moving object in a moving reference frame. So here's a nice clean carriage, and here's a brand new tennis ball for a photon. As the train moves along, the tennis ball moves up and down in alignment with the offside door. This is the periodic motion of the bouncing ball observed by both an observer within the moving train and also a stationary observer outside the train. However, the eyes of the outside observer are deceived a bit. When the train is removed, the outside observer perceives the ball correctly. The movement is represented by the two sides of an isosceles triangle. A vertical line from the apex will bisect the base at right angles. We'll call this line L0, and it represents the distance travelled by the photon tennis ball. The sides of the triangle represent the distance travelled by the ball to an outside observer, and we'll designate this CT, C being the speed of light for our photon tennis ball. The base represents the distance travelled by the train, and we designate that VT. Previous observers have identified a discrepancy in their observation of time. This observer has identified a discrepancy in his observation of space. Let's speed the train up to see what happens. To speed things up, we need a good light source like this laser and a fast train launched into space. The wireless modem will turn the laser on and off, and the mirror will reflect the beam back to the laser. In effect, we're just replacing the tennis ball with a stream of photons. So here we go. This red triangle looks harmless enough, but it does high-end damage to our perception of time. For the inside observer, the light travels up and down once. For the outside observer, it appears to take the long way round. In the special case of a 3-4-5 triangle, the light for the outside observer will travel 5 plus 5 is equal to 10 units. For the inside observer, it travels 3 plus 3 is equal to 6 units. So it's tempting to think that light travels faster for the outside observer. But light travels 3 times 10 to the 8th metres per second at a constant velocity in space. So we're left with the idea that there are 2 times, one for the inside observer and one for the outside observer. This puts an end to our consensus trance of a 24-hour Earth-centric time. We're now in a position to develop a formula for the 2 times. So we make the formula by using our triangle, and we get CT squared is equal to L0 squared plus VT squared. So we make L0 the subject, and that gives us CT squared minus VT squared. Now we can take a factor of t squared from the right, which gives us L naught squared is equal to t squared outside c squared minus v squared. We'll make t squared the subject of the formula, and we get t squared is going to be equal to L naught squared divided by c squared minus v squared. Now we can take a factor of c squared out of the bottom line, and we get t squared is equal to L naught squared over c squared outside 1 minus v squared on c squared. L naught on c is equal to t naught, our other time. So we now have t squared is equal to L naught squared on c squared, which is going to be t naught squared divided by 1 minus v squared on c squared. Finally, we take the square root and we end up with t is equal to t naught on the square root of 1 minus v squared on c squared. The two times, t and t naught, are radically different. Using a value of 0.99c produces a markedly different result. If we let the value of t naught be 10 years and the value of v squared be 0.99c, we get a value of 71 years. To put this in context, look at these skateboarding twins. The 20-year-old twin on the right takes a journey into space for 10 years at 0.99c, while the Earth twin stays home. The year is 2023. When he returns to Earth, he is 30 years old, but the year is 2094 and his brother is 94 years old. Who's the correct observer? The unsatisfying answer is that they're both correct. Time, remember, is a stubbornly persistent illusion that can be altered by the observer's frame of reference. To examine the effect of reference frame on perception further, we'll use two reference frames for the same trip between Mars and Jupiter. For the first reference frame, we'll use Mars, in which case the distance to Jupiter will be L naught is equal to v times t. In this thought experiment, the second reference frame is the train, so all events will appear undistorted in the confined space of the carriage. The designated time then is t0. So L is equal to V times t0. We have two equations from the same trip, so we can solve them simultaneously. From 2, we can say that L is equal to V times T outside the square root of 1 minus V squared on C squared, and we can say that since T is equal to T0 on 1 minus V squared on C squared. And from 1, which is L0 is equal to V times T, we can say that L is equal to L0 outside the square root of 1 minus V squared on C squared. This factor is always less than 1, so L will always be less than L0 in the direction of motion of the train. There are 3 fundamental units in physics: mass in kilograms, length in metres, and time in seconds. So far in our discussion, Einstein has obliterated the independent nature of 2 of these: length and time. We now check if mass suffers the same fate. To do this, we conduct another thought experiment using a 1 kilogram block accelerated at 1 metre per second. In other words, we apply a force of 1 Newton to the block. In the first second, it will travel 1 metre. In the second second, it will travel 2 metres. In the 300 millionth second, it will travel at the speed of light. The second after that, it will travel faster than the speed of light. But the speed of light is the ultimate speed in the universe. So what miraculous intervention will take place to slow the block down? It turns out that the block will require all the mass in the universe to fuel it beyond the speed of light. Relativity describes the relationship between mass and high speed as m is equal to m0 on 1 minus v squared on c squared. Once again, the bottom line will become vanishingly small as v approaches the speed of light, which means that m will become increasingly large. What happens to a photon travelling at the speed of light? The question now is this: can a photon have mass? And if it does, why doesn't it suffer the same consequences as the 1 kilogram block? We can analyse this question by considering a solar panel. The solar panel is cleverly designed using P and N type silicon, so the photons from the sun can release bound electrons and give them enough momentum to produce electric current. This process is defined by the equation momentum is equal to mass times velocity is equal to h on lambda, where h is Planck's constant and lambda is the photon wavelength. As well as being a vector quantity, momentum is conserved in elastic collisions such as this one. So h on lambda must be able to be disassembled into the units of mass times velocity. To do this, we need to do some detective work to see whether the expression h on lambda contains any units of mass. The forensic tool for this job is dimensional analysis, where we break the terms down into the fundamental units of mass, length and time. So we start with h. H has the unit joule times seconds. Joule itself breaks down into force times distance, which is work or energy. So that's force times distance times seconds. Then force breaks down into mass times acceleration. So that's m times a times d times seconds. Acceleration has the units, the fundamental units of length on time squared, meters per second per second. Mass has the units of mass, distance has the units of length, and seconds has the units of time. This t on the top line will cancel with one of the t's on the bottom line, which gives us m L squared on t. If we bring the unit of 1 on lambda down, that's 1 on length. Lambda is wave length. So we have 1 on length over here, and that will cancel with one of the lengths on the top line. So ultimately, we have m L on t. L on t is velocity, meters per second. So this is directly equal to mv, which is equal to p. So that expression does contain mass. What gives? What gives is this. A photon travels at the speed of light. Therefore, all its mass is stored as energy. This luxury is not afforded to all particles. An electron has a rest mass of 9.11 times 10 to the negative 31 kilograms. Therefore, when it's accelerated towards the speed of light, it follows an asymptotic trajectory in a similar way to mass. Finally, to consolidate these ideas, here are some salient points. While sound events do not always appear simultaneous on Earth, light events do, since light travels so quickly. Einstein's idea of simultaneous events involves light arriving at a point from two equidistant sources at the same time. 24-hour Earth-centric time is a stubbornly persistent illusion. Einstein's two postulates are: 1, all non-accelerating reference frames are completely equivalent, and 2, the speed of light is constant, independent of its source. These ideas led to the astonishing outcomes of special relativity. Time dilates, length contracts, and both momentum and mass increase dramatically close to the speed of light. I hope all this helps, and all the very best.